everybody, all the participants. Hope you enjoyed yesterday's two sessions. The first one is the theory and the second one was the lab. So today we have our day two session one theory session, and a warm welcome to our eminent speaker in quantum computing, Professor Prashant K.Panigrahi from Indian Institute of Science Education and Research from Kolkata. So thank you so much for joining us, sir. We welcome you all. So you can start your presentation, sir.
Okay, thank you, Sridhar, and
Thank you,
sorry
sir.
for the inconvenience.
It's
We
fine,
are
sir. Okay,
all
sir.
learning from technology, and
Okay, sir.
hopefully getting ready for quantum technology in near future.
Yeah, yeah.
Okay, so I'll be talking about quantum computation and technology, and I'll go very slow, even if you know quantum mechanics. But you will find out that the quantum mechanics that quantum computation requires is very elemental. The whole emphasis is on the basic principles of quantum mechanics. So I will sort of run through you the developments in quantum mechanics, which is coming in handy for quantum computing. So I can start from the early days. Okay. So now, as you know, for example, the old quantum mechanics, there are two parts. One is the old quantum mechanics, essentially Niels Bohr, solving the hydrogen atom with some kind of intuition, getting spectrum as minus 13.6 by n square, matching it with the spectral lines. So experiments have always guided quantum mechanics. Planck came up with distribution to explain black body radiation. Again, experiment, light. And observed spectrum of hydrogen, various kind of lines were fitted by Niels Bohr with a very pictorial kind of description, not very satisfactory. Drawing analogy from the classical world, solar system, that there's a sun, there's a planet going around, similarly there's a proton, there's an electron going around. But very quickly they came up with contradictions, that a moving, circularly moving or elliptically moving particle will experience acceleration. Therefore, it should emit light, but there's no light coming. Electron and proton together are very stable. So then it took, lot of experiments, and this Einstein's AB coefficient, Einstein's explanation of photoelectric effect, then this particle and wave nature together, Louis de Broglie, lot of concepts are developed. So important point from there is that particle and wave. So that is one aspect we should keep in mind. Wave and particle nature. Photon, which was a earlier wave, they discovered its particle nature. Okay. Second, electron, which was a particle, was found to show wave nature. So learning from there is this particle and wave duality. That is one thing which still remains to be solved. For example, there were experiments showing so-called pilot wave theory, as if electron is sitting on a pilot wave which is guiding it. That was Louis de Broglie, then redeveloped by Bohm, Bohmian trajectory. So that thing is still unresolved. Now, nature of light. See, black body radiation, thermal light. That is amazingly that is not understood. But laser, which is a miracle, right? Which is a simple Gaussian, that is actually classical light. So the laser, which was invented based on quantum mechanics, particularly using Einstein's idea, that 2016-17 kind of papers, is actually an example of a classical light. Therefore, if somebody tries to draw a single photon from laser, claims that it's a quantum light, answer is no, it is not quantum. It's very counterintuitive. This light from black body, light from sunlight, they are quantum. Whereas laser light, which is very fascinating, is classical, completely classical. And who showed it completely classical? George Larson. So these three gentlemen whom you are seeing, Schrodinger, Heisenberg, and Dirac, they played a very significant role. Heisenberg came up with the idea of matrix mechanics, and again, very intuitive kind of physicist. And you will find out in quantum computation, we use matrices left and right. So this matrix is something that keep in mind. Wave particle duality, then this matrix. mechanics which is now being used, and I'll show you examples. Now Schrodinger came up with wave mechanics. So that's 1926. There are two papers from Schrodinger which really used classical Hamilton-Jacobi theory to show a very close connection of classical mechanics with the quantum world. And until then, Heisenberg, for example, and his colleagues, Jordan and Max Born, they were thinking that quantum mechanics is revolutionary. It's completely different mechanics. Schrodinger said no. That opened the eye of everybody. So Schrodinger came up with wave mechanics, namely the differential equation solving gave you hydrogen atom. It was a remarkable thing. And all those methods of solving differential equations were known earlier, namely Laguerre polynomial, Hermite polynomial. They were all developed in the context of pure mathematics, basically vector space. So the concept of vector space is very, very important. You will find out. Heisenberg introduced vector space through matrices. Now the simplest example is spin 2 by 2 matrices, which Pauli introduced to explain again spectral lines. Each spectral line splitting into two. Right now we are using them and we are calling them qubits. So Heisenberg dealt with a much bigger matrix. The simplest version of that, a 2 by 2 matrix, is what your superconducting quantum computers are using. So IBM has many quantum computers available. You can log in there, do quantum computation. They are using the so-called qubits, which is the simplest example of objects which deal with 2 by 2 matrices, just plain 2 by 2 matrices. Who came up with these 2 by 2 matrices? It was Pauli to explain spin. And believe it or not, this development had a strong fit with Hamilton. Hamilton came up with Hamilton-Jacobi theory to explain waves, wavefront, how the wavefront with its arrows, which will how it propagates. So because it was the wavefront it was describing, it was easy from Hamilton-Jacobi theory to go into quantum mechanics. Now Schrodinger, although we are beginning to use continuous variable states, namely Gaussians, the hydrogen atom wave function, those kind of things we are still not comfortable. All we are dealing with in the IBM machines is what Heisenberg had found, the simplest example of 2 by 2 matrices. We call it qubit. So we last year and now slowly people are beginning to use this kind of object which Schrodinger invented, namely wave functions which are functions. A Gaussian is a function. So you can see how little progress we have done in the front of technology, although theory is understood. Now Dirac, for example, Dirac made things abstract, joined up these two approaches of Heisenberg and Schrodinger, and wrote that book in 1932, which is still being used. And particularly Dirac came up with this idea, which he describes. People are still, eminent people cite that sentence.
Excuse me, sir. Sorry to interrupt you. Some of the participants have got some issues because they are not hearing your voice properly. So I request you to please keep your microphone close to your mouth.
Yeah. How about now? Is it better? I'll speak more loudly. Huh?
Now it's okay.
Okay,
If your
good.
microphone is close to your mouth, then it's okay.
Okay. No, okay. So I hope they can also point out so that I will correct myself if there is.
You are not changing the slides right now, sir.
Right now, I'm not changing. I'm just
Okay.
beginning with the quantum mechanics.
Yeah,
and
sure.
Picking up the ideas which will be the key ideas, essentially being used in quantum computer.
Okay.
So some of you might have missed. So let me again repeat. From the olden days, before quantum mechanics, we got wave and particle. That is still being debated. Wave and particle. Then quantum mechanics around 25-26, quantum mechanics was formulated. From there, we learned about continuous functions, thanks to Schrodinger solving a differential equation. Those objects are now beginning to play. Starting from 2019, quantum computation is beginning to use so-called continuous variable functions which are due to Schrodinger. But so far, the machines which are available, like IBM quantum computer, they use matrices. Simplest example is 2 by 2 matrices. They are called qubit. Now, concepts, for example, is largely goes to Dirac. His book 1932, in the first one or two chapters, has this point that a single photon interferes with itself. Right now, that is where we are interpreting that what does it really mean? For example, if you take a double slit experiment, that is precisely where the physics is right now. People are trying to understand the simple double slit experiment. What is wave nature? What is particle nature? Okay. So very good. So Schrodinger came up with this word of entanglement, and in answer to the so-called EPR paradox, Einstein, Podolsky, and Rosen, they came up with this EPR paradox that I'll talk to you now, the quantum correlation, which is being used now. So very good. Now let's move to the next one. So what is Schrodinger equation? Schrodinger equation is this simpler equation. This object called a ket is due to Dirac, this notation. Because in case of Schrodinger's quantum mechanics or even matrix mechanics, psi dagger psi shows the probability of finding the particle. And that Dirac pointed out that if you have to take dagger means transpose of a matrix with a star, better to separate out this ket, which is a column vector, in our case simplest column vector. Column vector with two entries, 1 0 1 0 1. 1 0 is called 0 1, both are called qubits. So these kind of equations, the Schrodinger equation will play a key role, and Hamiltonian is the one which will give you evolution, how the things change in time. So there are, you'll find out quantum computers are using this. For example, there's a computer called D-Waves. It is located, company is located in Canada. It uses this Hamiltonian evolution to solve your classical problems. Whatever problems you have, you can actually load into that computer, the so-called D-Waves, through a spin Hamiltonian, and it will give the answer for you. If you want to do factorization, 21 is equal to 7 times 3. You have to load that problem into a Hamiltonian called Ising model Hamiltonian. It will do the evolution and give you the answer. So, okay. So, these two aspects, please keep in mind: matrices and differential equations. Time evolution through a Hamiltonian. Okay. So now while we are doing it, you have to solve the problems. While solving, this time evolution is something which people always find difficult to solve. You can solve explicitly. Most of the problems are difficult. People come up with pictures. You'll find out that these kind of words, Heisenberg picture. In Heisenberg picture, you don't care about the wave function. You look at the operators. Like in real life, the operators really do everything. You can make them time dependent. Forget about wave function. Wave function remains fixed. If it's a qubit, 1 0, it remains as a qubit. Everything happens to the operators. You can also deal with it, because remember, quantum mechanics is very strange. Now Schrodinger pointed out, well, the best thing would be to make those wave functions, because they're functions, time dependent. So that is his picture. So either you can deal with this or you can deal with it. That is up to your convenience. Now, very interestingly, most of the time you have to deal with interaction picture. Why is that? Because Hamiltonian will have, you have to take advantage of both the approaches. Wave function evolving in time, operator evolving in time. You find out that what we do in quantum mechanics is that we take advantage of that. That is due to Heisenberg, so due to Dirac. What he said is, look, given an Hamiltonian, if it is interaction, you cannot solve the whole Hamiltonian. You can solve part of it. Call it H0, the solvable part. Use that wave function and remove that time evolution, because we know how to deal with it. The residual time evolution coming due to interaction is the thing we should concentrate. So the part which you know the answer, that answer part you remove. That time dependence you already incorporate because you know the answer. Over and above what will happen due to interaction, you take it. So why am I saying all these things? Because now as you deal with quantum computers, you will find out that people are using states, the so-called wave functions. You will find out two kinds of wave functions is being used. One is so-called qubit, or multi-particle system representing multi-qubit, and you will find out continuous variable states like Gaussians, product of Gaussians. So you should know that both are coming from quantum mechanics. One is dealing with discrete degrees of freedom like spin, which can take only 2 values. Angular momentum 1 can take 3 values. So there are class of variables taking finite number of values. They also exist in quantum mechanics. They have also Hamiltonian. In fact, spin precedes in the presence of magnetic field. Hamiltonian or energy is minus mu dot B. mu is the magnetic moment, B is the magnetic field. So that evolution of the discrete states takes place through this kind of Hamiltonian. But if you have a charged particle, like for example, proton with an electron, which is hydrogen atom, they interact with Coulomb force, and that wave function is a continuous variable. It is an exponential function with a polynomial. If you deal with it, you have to deal with that Hamiltonian, which is continuous variable. Kinetic energy plus potential energy. Potential energy minus E square by R. So both the things are being used. This right now there are two functional quantum computers. One is a version due to D waves. They use this Hamiltonian on spin system, and evolution takes place through that. Whatever problem you ask, they will put it in the Hamiltonian as basically put the question through the Hamiltonian. Evolution will take place. At the end, you will get the answer. Now, IBM, for example, has a number of versions of a quantum computer. They use finite degrees of freedom, namely this kind of spin things. So very good. Now, while you are finding the time evolution, interaction comes in. Now, question is how to deal with it. As I told you, the so-called interaction picture is the one which is being used now. Part of the Hamiltonian you can solve, you eliminate that part, make the wave function time dependent due to that part only. Over and above, whatever little bit of interaction remains, you treat it in perturbation theory. That seems to give good answer. So very good. Now you may ask that, in a quantum computer, how do you see? I'll show you some architecture. What happens is that you take this, whatever computer you have, this classical computer. In classical computer, what you find? You have small islands. Okay, so those small islands, they are like your, where you store the voltage. In classical computer, you deal with numbers. If there is no voltage, it is 0. If there is 1 unit of voltage, some amount of voltage, you call it 1. So by charging and not charging, you introduce this idea of 0 and 1. And then furthermore, you have a little bit of mathematics. 1 plus 1 becomes 0. So this is the mathematics, mod 2 is the one which is used, and apparently people showed very clearly everything you can do. So this is, if you have a microscope, you can really go and see a circuit in a classical computer. At the basic level, you will find out units which are being charged. No voltage, and they connected with each other. All the problems, factorization, even doing hydrogen atom molecular energy, hydrogen molecule, all those things you can do using classical computer. So what is the advantage quantum mechanics gives you is that, first of all, disadvantage. Instead of numbers, you deal with matrices. Wherever there's 0, you call it C bit, you put 1, 0. It's a column vector. Wherever there's 1, put 0, 1. So instead of numbers, you deal with matrices. That's the first thing. Now, because of that, matrices are a bit more complicated. So that is the reason that first complication you have to encounter in quantum mechanics. Then they become vectors. You'll find out that whatever you have learned, vector addition in your college physics, to start with vector A plus B, when you add, you get vector C. Am I audible? Sir, am I audible?
Yes, sir, you're audible. Participants, I think one of the mic is on.
Okay. All right.
Yes,
so
you
as
can
I
carry
told
on.
you now.
I have muted. Okay.
Yeah. So now let me, as this I have mentioned to you. Look, for example, in a classical computer, you have a regular 0. You see, no voltage is called 0. It is called a C bit. 1 unit of voltage is 1. So first thing you do, for example, if you go to IBM architecture, you will find out in the architecture wherever there is a 0, they will put a matrix, column vector 1, 0. If it is 1, 0, 1. So that is the simplest replacement, and quantum computing you can do using them. But the moment matrices comes, as I told you, you can add them. Vector addition, standard vector addition. And complex numbers come in an essential way. For example, we got introduced to complex number by taking the square root of -1. So before quantum mechanics came, complex numbers were there. And quantum mechanics, they found a natural application in the sense that you cannot avoid. This object have to be complex. Because if it's not complex, you cannot have interference. So these alpha, beta are complex numbers. Now you have to do something called normalization. Means if there is one electron having spin up or spin down, if you superpose them, you should get still one electron. Therefore, psi mod square, namely the total probability, should be 1. So if you find out if these are actually like vectors, if you take 0, if you take this dagger, it becomes a row vector with 1, 0. Then you can check. Ket bra 0, ket 0 will give you 1. Bra 0, ket 1 will give you 0. That means they are orthogonal. But this vector concept we knew in terms of normal vectors, which has 3 components, x, y, and z. Suppose if you take a vector A, it has ax, ay, az. You have unit vectors, small I, small j, small k. So we are familiar with this kind of mathematics from our vectors. We have studied vector space. Same idea comes here, except they are complex numbers. So you see, vector space and complex numbers. These are the mathematics which you need. So vector space specifically, we need matrices. If you go to continuous variable, these objects become functions. So you see, so that is the requirement. Matrices, linear algebra, vectors. Right now, if you know these things, you have enough. You can contribute to quantum computation in a very significant way. Very good. So now, just having qubit is not enough. You have to do some operation. In classical computers, for example, there are many operations available. You people are more familiar than me. Fortunately, in quantum computers, you need only 2 matrices. Others you can employ. They, so they are called so-called Hadamard and control knot. I will explain to you in the next slide or subsequently. But you will find out from good old quantum mechanics, whatever old we knew in the context of spins, the same mathematics we picked up. We can use this also as a gate. For example, look at this object. This is Pauli's sigma x of matrix 0, 1, 1, 0. They came to describe electron spin. You can check. If it acts on 0, it will take 0 to 1. If it acts on 1, it will take 1 to 0. 0 is equal to 1, 0. You can multiply here. So what it does, it exchanges particles. Sometimes that is required because you would like to exchange the particles. So if you want to exchange 0 with 1, take this 0, apply this gate x on it. It will become 1. So it is useful. Now one thing please remember, in quantum mechanics, whatever has to be done with a unitary matrix. Because as I told you, the probability has to be conserved. Psi dagger psi has to be 1 all the time. Even if there is time evolution, if there is no loss. The word we use for loss is called decoherence. If there is no decoherence, probability is always conserved. So if psi changes to a matrix U, because psi dagger psi must remain invariant, U dagger U must be 1. Same as U dagger. Therefore, this matrix has to be unitary. Fortunately, this matrix is unitary. And it is also Hermitian. Most of the quantum mechanical observables, what we measure, like energy, momentum, they should be real, because in the real world we see energy. For example, 1 electron volt, 2 electron volt. Since we find real world energies are numbers, these operators are taken to be Hermitian, because if you find their eigenvalues, they will be numbers. For example, real numbers. This object has eigenvalues 1 and -1. So same from Pauli, we picked up this sigma z matrix. We only gave a new name. Sigma x, we call it x. This notation is due to computer science people. They used earlier get x, z. They just changed this object to their name. What this fellow does, it keeps 0 as 0, but changes this fellow sign to -1. That is also required. Sometimes you would like to interfere with a minus sign. So this phase change has to be allowed, and this is the matrix. Unfortunately, the mathematics is fairly simple, 2 by 2. We knew all those things dealing with spin. So far, only we change the names, and we are dealing with quantum computation. All right. So now, I will introduce you to the first important gate called Hadamard. The Hadamard name came from the person called Hadamard, old mathematician from 1900 kind of thing. So he of course used this thing for matrix operations. But for us, it's quite handy. What it gives? It gives superposition. You see, this is a matrix having 4 entries, 1, 1, 1, -1. You can check. The earlier matrix took 0 to 1, 1 to 0. This for what it does, it creates 0 to 0 plus 1, 1 to 0 minus 1. So please remember, this is a very, very important thing. So I would like to emphasize once more. Superposition is key to quantum mechanics. Waves also show superposition, interference, diffraction, all those things arise because of superposition. Okay. Now, superposition gives you something called quantum parallelism. You have two channels available, two parallel process. Simultaneously, if you put more of them, you can actually parallel process in many channels. So this is the power which comes to quantum computers through superposition. This is a key principle. Please remember. So the superposition is possible because the states are vectors. So Hadamard is a single qubit operator. This gate acts on only one qubit, produces superposition. So this allows you to find out multiple channels. That is possible through this. This fellow goes to this fellow goes to that. Now, if you are familiar with light, you will see these things are all known in light. Whatever we are dealing so far is actually polarization. If you read Hecht, you will find out any optics book, polarized light is using this kind of mathematics. For example, light, if it's moving along z direction, it has polarization along x and y. If it is x and y, you will find out the states are this. Actually, here we call them a z eigenstate because they are eigenstate of sigma z, capital Z. That's what I kept there. But in optics, they are the two polarization. And these two are the polarization along 45 degree and 135 degree. And you will find out there is another matrix which I am deliberately not writing called sigma y, 0 minus I 0. Those eigenstates you will find out are actually circular polarization. So if you are familiar with optics, particularly polarization optics, you will find nothing new here. Linear polarization, polarization 45 degree, 135 degree, and circular polarization. That is what we are dealing with. We Hadamard denoted as plus and minus. So you can actually, because of the sign, plus here, minus here. So please remember that whenever you read a paper, you will find out this object is called computational basis. Computational basis, because computation is done using these vectors. They're called basis set. Basis set means in 2 dimensions you need 2 vectors. So here are they. There is some language called orthogonal and completeness. And what is orthogonal and completeness? As I showed you, 0, 0, if you take 0, which is dagger of this, times get 0, you find to be 1. That means normalized to 1. Same thing for 1. 0, 1, if you take, the dot product will be 0. You take, for example, dagger, which is 1, 0. This is 0, 1, multiply them. Dot product is 0. So whatever you knew, A dot B, mod A square, the same idea here. Unit vector I square is equal to J square is equal to K square is equal to 1. So these are like the unit vectors. So since they are unit vectors, any arbitrary vector you can expand in terms of them. That's what I showed you. Any arbitrary vector psi is alpha 0 plus beta 1. Psi is an unknown state if alpha beta you do not know. So that is actually useful because you will find the first application of a quantum computer is that you can actually teleport. The Star Trek movies we have heard that human beings are being teleported from one planet to the other. Here, same kind of thing you can do. You can teleport unknown state. State is completely unknown. You can actually teleport. How far people have done it? Is it possible that it has been done experimentally? Answer is yes. For example, you can check things have been teleported across the Danube in Vienna, and there is a group which has teleported things from one side of the river to the other. For example, there are Chinese experiments showing teleportation in kilometer scale. So teleportation has been done. So this good old name plus minus you will find computational basis, Hadamard basis. This language you will find everywhere. Computational basis, Hadamard basis, and Hadamard operator. And this is called a single qubit operator. Very nice. Now, single qubit is not enough because when you try to solve a problem, you have to involve more gates. Like you have to involve more people. So now this is the other one which we need called control knot. Why it's called control knot? I promise I will not go anywhere beyond 4x4 matrices. and you don't need also. First of all, if it's a quantum operation, it better be unitary. U dagger must be equal to U inverse. You can check that is true. U dagger is equal to U inverse. Now what it does? It takes, if the first input is 0, second input is 0, nothing happens. It remains 0, 0. If the first input is 0, second is 1, nothing also happens. Basically, if the input is 0, nothing happens. If the input is 1, then changes take place. Control. The word control comes from there. If controlled by 1, if the entry is 1, then there is a negation. 0 becomes 1. If the entry here is 1, becomes 0. So this negation comes controlled by the entry. If the entry is 1, change will take place. Entry 0, nothing will happen. Now you might be wondering, what is this object 0, 0? I introduce only 1, 0. Call it ket. Name is due to Dirac. Now I have put this 2, 0. These 2 zeros are actually matrix multiplication. Simple matrix multiplication, direct product. 1, 0 cross 1, 0. You take this mathematics, like direct product. Mathematics people knew because they wanted to solve. For example, for if you solve linear equations, for example, where did we come across matrices? You want to solve 2x plus 3y is equal to 5, x plus y is equal to 1. You cast it in the form of a matrix. You can solve it much more easily than by brute force. That is how matrices came. Inversion came. So initially they are dealing with 2 by 2 matrix, then came 4 by 4 matrix. Then they discovered that 4 by 4 matrix can be described using 2 by 2 matrices, like a big house we build using small bricks. So these are the qubit. Now what's the advantage here? It describes 2 particles. Where do you come across 2 particles? You go to helium. In helium there are 2 electrons. This is the state that describes that. If the 2 electrons are in the magnetic field, they will point along the direction of the magnetic field, and that is deciding the state. If they are pointing down, then this is 1, 1. If 1 is up, second is down, this is this state. Now, if first fellow is up, down, second fellow is up, then this is state. So this describes a 2-particle system. You can generalize, you can go to more number of particles, you can also describe single particle, but as you know, a single qubit cannot do much computation for you. What it can do? It can store information. How did it store information? That is what was pointed out by Feynman. Because as I showed you, you can have superposition, 0 plus 1. If you want to store information, you have to store 0 plus exponential I theta times 1. The page will keep information. That is what Feynman pointed out, that huge amount of information can be stored. Now, there is a peculiar thing. Because in quantum world, this state itself is not very meaningful. Its magnitude, namely mod square, is meaningful. Now, as you know, for example, if you take a mod square, if there is a phase, exponential I theta, it will cancel. Because psi star psi. If it is exponential I theta here, there will be exponential minus I theta there. So in quantum mechanics, there is some sort of arbitrariness. If you are dealing with the states, overall phase you cannot measure. But if you put the phase in between superposition, 0 plus exponential I theta times 1, that you can actually retrieve through measurement. Experimentally, you can actually retrieve that parameter. Now the question arises, how much of phase you can distinguish? For example, if it is exponential I pi by 2, if it is exponential I pi, can you really distinguish? For example, 0 plus 1 with 0 minus 1. One has to be a bit careful. That question has been analyzed by a gentleman called Volevo. So how much of information you can extract? There is a lot of theorems, a lot of proofs in that direction. So many of these classical mathematics which are known, for example, Shannon's theory of information, there are now quantum verses coming. So I just let me point out to you, keep it in mind. Although Feynman was optimistic, it was pointed out that in the quantum world there is a limit called Volevo bound, how much of information you can extract. So therefore, information theoretic people are also coming into picture. So quantum computation is an area you will find computer scientists, mathematicians, statistics person, physicists, chemists. Now it is going to biology, because biology they have discovered photosynthesis uses quantum coherence. To understand that, quantum computer is being employed. So in this quantum computation world, you will find people and experimentally theoreticians of all sorts who are doing meaningful contribution. Therefore, you can also do meaningful contribution. Fortunately, mathematics is not very difficult. Simple matrix, load up quantum mechanics. Here, all you need is have a good understanding of the that's enough. Very good. This is a bigger computation. Computational in this product space, two particle space. What is dimension of it? It's a column vector with entry 1, this entry 1, 0, 0, 0, this one. And this fellow would be 0, 1. This is this object. 1, 0 is this object. Sorry, this object. 1, 0. 1, 1 is this object. You see? So these objects are nothing but here. And this control knot negation is composed of this. You convince yourself because the first two fellows are diagonal, 1, 1, because of which these two are not affected. You can check that because this is 1. This fellow, what it does, it exchanges 0 to 1. You see this exchange operator, if you remember, I introduced you 0, 1, 1, 0. So if this, that is what, it's changing 0 to 1 here, 1 to 0. And it happens because 1 is present. That comes because these two zeros are here. So you convince yourself that this kind of gate designing, you can actually make it bigger if you want. But to our good luck, almost everything you can do only using Hadamard and controller. Hadamard is a single qubit operation, creates linear superposition. Control knot is a control negation, is a 4x4 object, lives in the two particle world. There are two particles. And because otherwise, what is the meaning of knot? You can control knot will act if there are two particles. These two are enough. This I will show you creates entanglement. You can actually entangle people. Now you might be wondering, why am I coming up with a new word called entanglement? Apparently this word is not new. Schrödinger knew it in 36, 37. He in fact used this German version of the word entanglement. That was in answer to Einstein's EPR paradox. Now people then slowly found out, you might have also found out, these entangled systems are everywhere. For example, if you look at hydrogen molecule, para-hydrogen, ortho-hydrogen, there are two electrons in spin state of singlet or triplet. You convince yourself they are actually examples of entangled state. Okay, entangled state means you cannot separate them. See, for example, here the examples which I have given are very simple examples. If it is 0, 0, you might write as 0, 0 as a two particle state, or you can write 0 and 0. So you take 0 as 1, 0, this has 1 zeros, they are separable. Multiply them 1, 0 times 1, 0, you come across this. So as long as they are separable, whatever you do here, nothing happens here. This is also separable. Whatever you do here, nothing happens here. When I say whatever you do here, whatever you do here on the first particle. Okay, that is basically apply X operator, all the single qubit operators. Hadamard operator, Z operator, nothing will happen to here. But they see control knot. It essentially deals with two particle system. Because it is dealing with two particles, it has a, it is a nosy object. Like, try to poke nose in other person's thing. If the entry is 1, if, for example, then this will immediately change this color. So intrinsically it is affecting, and that is what it will create non-separability. You will see. So this concept of particles being separable or non-separable plays a very key role. And you can imagine if there is no connection between them, they're separable, practically you cannot do much using them. So for quantum computation, you need entanglement. You have to create entanglement. And what is the problem? Problem is that this entanglement gets very easily affected. Environment, outsiders can create disturbance, because of which quantum computers have to be pulled, separated from the environment. Otherwise, all the quantum computers what we have now, there is a problem, huge problem of difference. Interaction spoiling entanglement. Because of that, the computers are not very powerful. They are called, now what we are doing right now is called NISP. Okay, noisy. Basically, in computation, quantum computation in a noisy environment. people are trying to see, but still you can do in a quantum computer in a noisy environment. And that noise is coming because of environment, because quantum states are very prone to noise. They have to keep at low temperature so that they don't get affected. If you see, search for D-Wave computer, you will find a picture of that. Search for IBM, you will find they are all kept at very low temperature. Liquid nitrogen, liquid helium, so that environment effects are minimized. So to summarize, to do quantum computation, you need more than one particle. But building blocks are so-called qubit. In case of classical world, they are numbers 0 and 1. Addition was the mathematics. Here they are vectors, column vectors in matrices or regular vectors in case of continuous variable quantum computation. So you need all the vector properties, linear superposition, magnitude, dot product, and fortunately we knew these things. Matrices also new in solving linear equations, and that's the one which we use. So this direct product thing also is known to describe two particles. Like for example, 2 electrons in hydrogen, 2 electrons in helium. Now, if you have a magnetic field, you both are pointing along one direction, you can write it in this way. For example, up, they are separable. Any operation at this level doesn't affect this fellow. But more general states come into picture from experiment, like for example, 2 electrons in helium, 2 electrons in hydrogen molecule. They are something where this is not true. They are like singlet or triplet. You will find they are actually entangled, called maximally entangled state. So this kind of state, simplest hydrogen molecule, these 2 electrons, they have been bothering Einstein ever since this object came into play. Well, you may think experimentally things are observed. What was the thing he was bothered about? I'll show you that botheration came because the experimental output, when you measure something, what happens to the other? That paradox is going on. But fortunately, when engineers came into play in 90s, they showed the same paradox, EPR paradox, Einstein-Podolsky-Rosen paradox, can be used for teleportation. As I told you, teleportation which we have achieved experimentally is due to use of EPR paradox in technology. And that is the technology right now which is people are working. Best teleportation, teleportation Danube, on using optical fibers. So teleportation, unknown state can be teleported. Why do you think people will be interested? Because message will remain unknown. President will tell that this message, please send it to Prime Minister, so that nobody should read it. Now, an unknown state, it goes, teleports to Prime Minister, really nobody can read it. And unfortunately, in the quantum world, nothing can happen. The state will exactly go to Prime Minister, and he would know if somebody has tampered with. So this is the fact that tampering can be detected, unknown state can be teleported, communication can be done through quantum key distribution, are the ones which is now propelling quantum technology. So very good. Now let me show you the use of this control node and Hadamard. So very good. So these kind of circuits, for example, if you go to IBM, you will go to their computer, you will find out there is a thing they use called QSKIT. They are training people all over to do programming using quantum computer. So you can solve many problems using their quantum computer. It is free so far. Machines are free. You can play around. Our students are doing that. You will find this kind of circuit. This looks like good old electronic circuit. So here is the resistor 0. Every resistor is first to start with is 0. Whatever you want to do, you can do. You can actually pull these gates. IBM, if you go, you can actually from their pull, you can drag this pole and put it here. This is the notation for Hadamard. It always acts on a single qubit. The single qubit is evolving as a function of time. So Hadamard is the operator here, single qubit operator. This is the register. All these things are initialized at 0. Initialized at 0. That is the language they use. Then apply Hadamard. What it will do? It will actually create superposition. 0 will be taken to 0 plus 1 by root 2. Now you do a little bit of mathematics. You do control node. So what did you find here? You find here that 0 plus 1 by root 2 is here. Direct product with 0, that is the input which goes here. Apply a control node. What is control node? If it is 1, 0 will be changed to 1. If it is 1, and the second particle is in the state 1, it will change to 0. So this is the notation you use. Hadamard is a square bracket with H. Control knot is something which is a black dot, basically showing who is controlling whom. Second fellow is being controlled by the first fellow. If the first fellow's output is 1, if it is 0, it will change to 1, which is 0 here. That will change to 1. Okay, so you can check. Just take this 0 plus 1 by root 2, because after applying Hadamard, it becomes 0 plus 1 by root 2. At this level, there are two terms, 0, 0 plus 1, 0 divided by root 2. Root 2 is for normalization. Now control knot. If you do control knot, there are two terms, 0, 0, nothing will happen, 0, 0, 0, 0, 0 with a factor of root 2. The other state, 1, 0, which is the state here, you see. Before I did control knot, this is my state. 0 is this 0. This 0 plus 1 by root 2, I wrote it in this way, is this state. You can actually write it as a separable one. 0 plus 1 by root 2, that is the first particle, this state, times 0. That's what is written here. Now do control knot. This fellow is not going to be affected. This fellow will change. Here there is 1, 0 becomes 1, 1. And that is control knot. What is this state? This is called Dale state, example of a maximally entangled state. You cannot separate it out. Whichever way you try, you cannot write it in this way. Suppose somebody gives me this state, I can easily write it as 0 plus 1 by root 2, the first particle, times 0, the second particle. They are separated. Whatever you do locally here, not going to change. But this control knot is a non-local object. It changes. It is a noisy object. It tries, if there is something 1 here, it changes this flow. And that creates this and binds these two together. Now this is non-separable or entangled. You cannot write it as a product. So separable and non-separable, that's the word. Once it comes non-separable, then the concept arises, how much, what is the measure? So you'll find out, I may not work it out here, there is a measure. You can compute using old matrix algebra, this taking the trace operation, and this state is actually a maximally entangled state. It has one unit of entanglement called 1 EBIT. Like 1 kilogram entanglement is measured in 1 EBIT. And that mathematics is due to von Neumann. So you can actually take the so-called partial trace. Let's not get into it. There are very simple ways of doing it, and if some of you are interested, today we have a evening session on this kind of thing in our conference, QIQT 2021. In the end, I'll tell you about that. You can attend also. So this mathematics is very tractable. But all that I wanted to say is that in a big quantum computer, you don't need anything else except Hadamard and control knot. Other gates you use it for convenience, but everything can be done here using this. And this is a single qubit operator, creates superposition. Namely, it allows you to do multitasking. Superposition is essentially parallel processing, multitasking. Instead of one party, there will be two of them. Instead of one hand, there will be two of them. So parallel processing can be done. Control knot is a character which lives in the two particle world. And that creates entanglement. It creates non-separability. And fortunately here, it creates a maximally entangled state known in the name of John Bell state. What is this object? This is our measurement, electronic measurement. And readout, we read this output. So this line is for readout, this is for the register, this is the measurement, process of measurement. These are the kind of diagrams which you will see in a quantum computer or any paper you read. Very good. So this is the paradox which I have been referring to. If PR paradox came in, I think, 1936 or 37. What was Einstein bothered about? Einstein was bothered about this fact that if you measure here something, you will find, for example, they use the name Alice and Bob. If Alice is living in Delhi, if she measures her spin, whatever output she finds, Bob's output will be basically controlled by her. Now, even if it is in Washington, when it is in Moon, instantaneously Bob will change. Einstein was bothered about that. How much this instantaneous change, these particles are intertwined, namely entangled. Both the particles are connected to each other. There is a correlation. He was bothered about that. Let me show you that. Okay. Once more, for example, here I can show you. Suppose this is a superposition state. Does it exist? In nature, it doesn't exist. It is created in the laboratory, like NMR, nuclear magnetic resonance. Now you see here, this object is Alice. She lives in Delhi. Now there are two terms. 0 here, Alice here. Sorry, 0. Alice has two states, 0 and 1. Now this is superposition. So if Alice measures in Delhi and finds her state to be 0, what will be Bob's state? Bob's state will be 0. If Alice finds state 1, what will be Bob's state? Bob's state will be 1. So this instantaneous thing, that without any time delay, the moment a measurement is done in Delhi, the state changes to 1. That is what bothered Einstein. There is a lot of debate going on between Einstein and Bohr. So from that old school, Niels Bohr's school, two things came out, which are now becoming very handy. One is result of measurement. You can see from here. Now when you measure, then measurement leads to collapse of the state. Before that, it was superposition, sum of two terms. Now, because of the measurement, you see, if these two states collapse to 1, if the Alice result is 0, the state is only 0, 0. The two terms are gone, only one fellow has survived. If Alice state is 1, then the state collapses to 1, 1. This fellow is gone. So superposition is lost due to measurement. And measurement can be local or they can be global, in the sense that measurement can take place using both the qubits. Let's not get into it. Right now, measurement is local, only Alice measures. So it's like, for example, if you have a vector A, you want to find out its projection. That's what measurement looks like. Optics, polarizer and analyzer. Suppose if you have light, you can polarize it by putting a polarizer. Then you try to measure what kind of polarization by putting an analyzer. Same thing you do here. This is polarization along x direction, for example. This is along y direction. So this is exactly the polarization state of light. Except in a classical thing, outcome would be different. In the quantum world, the state will collapse. This collapse of the wave function came from Niels Bohr's Copenhagen school. So measurement leads to collapse of the wave function. That has survived from Niels Bohr's correspondence, and the other one was correspondence principle. How to come from quantum world to classical world. So this average value, so-called Ehrenfest theorem, connected the quantum results to classical world. So-called correspondence principle. S bar going to 0 limit, quantum thing will match with classical. So these two have survived from the Niels Bohr school, Copenhagen, interpretation of quantum mechanics. Now they are being used. Collapse of the wave function. Where are they used? Of course, when you measure, obvious outcome would be that there is no choice, but you can do more. You can actually design a quantum computer using this measurement. That if you do measurement, state will change. For example, it was 0, 0 plus 1, 1 before. Now measurement leads to either 0, 0 or 1, 1. So state is changing. That can be used for carrying out computation. There are in fact machines now available. People have shown experimentally that measurement induced change can be used for quantum computation. Okay, this is one aspect which is not there in the classical world. Another thing, suppose we are here. Suppose somebody, instead of Alice, somebody measures the villain called Eve, then state will collapse. Then Alice would know, Bob would know the state has collapsed. There is no connection between them. That means somebody is playing around. There is a thief there, or there is somebody which is hacking onto your computer, quantum computer, extracting information. Goes by the name of Eve. So-called eavesdropping can be detected. That is another thing that comes out of the quantum machines. That if you try to, if there is Eve does not know what the state is trying to see, you will leave a signature. This is not possible in the classical world. So because of which this quantum communication has become a big deal. So in banking sector, for example, you exchange information through something called a key. When you are doing a transaction, there is a process where whatever number you are giving is being encrypted. And for that encryption, you generate something called a key. For example, when you do OTP, a key comes to you, 3601. Then you use that. So this quantum key distribution is something which comes from measurement. And if you did, for example, the first one was Bennett and Brassard, 1984, only based on measurement. So measurement has come very handy, and this uncertainty that when you change, measure, things will change. Those the aspects have been used. One is for abstract computing, called measurement-induced quantum computing paradigm, new way of doing computing, which has been shown that it works. Other is measurement-induced changes are used to detect Eve, to securely send information from one party to other. That also is now available, that market. You can search QKD. Last year I had checked, it was around $10,000. There are 3 companies. Now maybe more. One Chinese company is there. You will make it things cheaper. So quantum key distribution. You can generate key to encrypt your message and decrypt it at the desired point. This quantum technology has already been there in the market. Or what is the other thing? Other thing is that this collapse is completely arbitrary. If you measure 0, when you will you get 0, when you will you get 1, you do not know. Completely arbitrary. Half of the time it will be 0, other half will be 1. So this has been used to generate random numbers. Quantum random number generator, because complete random output, that is also being used now. For example, USA is broadcasting quantum random numbers. If you want to do a MATLAB program where you need sometimes to use Monte Carlo simulation on random numbers, now you generate it through RAND, /RAND, RAND. Instead of that, you can use the random number what the USA is generating. Now those are quantum random numbers. They come from this. So because of which I told you that statistics people are now playing a big role. What they do? They check if it is random or not. If you check, see, for example, IISERKolkata, you will find a lot of statistics people are coming up with algorithm to check randomly. So everybody is in business. Computer people are in business. They are using a new paradigm to do computation, albeit in a quantum platform. Statistics people are there to check if the number is random or not. Machines are available. You can sell in the market. This randomness is used for generating key. Bennett and Brassard. Bennett was the computer science head in IBM. Brassard was the electrical engineering professor with mathematics background in Montreal, University of Montreal. No physics. They came up with quantum key distribution. Same Bennett in 92 showed that this EPR paradox, basically using this state, can be used to teleport an unknown state. So these are the kind of things you can see. Engineers have used the basic principles of quantum mechanics, nothing more, superposition and measurement leading to collapse of the state, and measurement in different bases, which you knew. For example, we can measure in r theta by basis, we can measure in Cartesian coordinates. Those things are being used now. So quantum computation has not gone beyond the first chapter of any reasonable quantum mechanics. Now you look at Dirac's book. After introduction, he talks about interference through single slit, double slit experiment. That is where now people are doing experiment. So it has not gone very far ahead because technology takes time, experiment takes time. And quantum world is very fragile because of decoherence, things change. Therefore, making things sure and results certain is not an easy task. We need better engineers. Okay, so this is what I was telling, that moment Alice detects something, Bob's state will collapse. That is what was bothering Einstein. This is the famous paradox all about. Lot of debate. In fact, Schrodinger came up with the word entanglement, describing this. So it stayed for a while. Only in 60s, John Bell, who happened to be a particle physics person in CERN, he tried to quantify it. That if it is really quantum, can I come up with a measurement or something which can be tested? So he actually showed using mathematics which was invented 100 years back by a gentleman called Boole, B-O-O-L-E, that if it's classical, you can actually do some measurement that will give you results which will lie between -2 to +2. If it's quantum, it will lie between -2√2 to +2. That was his contribution. And then people actually did experiment. I think it was an aspect. Yeah, and there are lots of experiments going on now. Various kind of loopholes were there. They have all fixed. Quantum mechanics works. So these are the kind of experiments you can see the apparatus. Because the quantum world is very fragile, you have to protect them in cold atmosphere, you have to generate single photons. These are the kind of things which are used, and then detect. You see these kind of things, experimental people use. I gave an arrow. They use this kind of thing for detection. And what is the subject? This is a crystal, which one light comes, splits into two. So these are the kind of, and what does this imply? Polarization, circular polarization, and clockwise, anti-clockwise. You see, plus, minus. Sigma matrix I mentioned to you, Pauli. So this is a physical related paper. So this kind of notation is not very light comes out. Most of these things are done by light. Light comes out. Then light is manipulated. Here there's a mirror, detected, polarization state, and these are atoms. Whatever spectroscopy for example, S half. This is probably rubidium, if I remember correctly. So if that is spectroscopy, what we have learned earlier, these are the kind of 3/2 state. And there is an excited state which is like a resonance. This notation is from spectroscopy, S, P, F, and you can put a magnetic field, separate them. M is your azimuthal quantum number. So you see, these are the kind of experiments people are doing. Entangling operation, I told you, control knot. Then light pulses are used, laser pulses are used. This is also called polarization beam splitter, like your calcite crystal, ordinary, extraordinary beam. These are the kind of things people are actually using. All right. So now, okay. So now, this is the first experiment, 1982, very famous one, Alan Aspect, French experimentalist. So what did Bell do? He found an inequality. Two operators. He took basically spin degrees of freedom, sigma x and sigma y, only two. Took the entangled state, and for Maxwellian entangled state, which I have introduced earlier, he found the expectation values of these two sigma operators are actually 2√2. And that's what was checked. Classical world, it will always lie between 2 and minus 2. So the statistics person who had proved it was Boole. That was in 1800 odd or something like that, if I remember correctly. Very good. So now, so how do you, for example, there is another very peculiar thing. If you take a quantum particle which is pointing along, let us say, z direction, if you are measuring along x direction, if it is classical light, you should not see anything because 90 degree. So your light is going polarization along z, you are measuring along x or y. Classically, this vector will have no component there, it will find 0. But in quantum world, very peculiar. You will find it actually. What will you find? You will find half of the times it is along x plus x direction, other half is along minus y direction. Now, if you do large number of measurements, the average polarization will be 0 because plus will be plus, minus will be minus, it will be 0. That is like your classical result because this polarization is pointing along z direction and you are measuring along x direction, you should not see anything. But in a quantum world, you will see. That is the main thing. It will see. You will see either along plus or along minus. How many times? 50%. This you can test in IBM quantum computer. Create a state along plus minus, which I gave that notation, 0 plus 1 by root 2, 0 minus 1 by root 2. Measure along z direction, namely 0 and 1 basis. You will find half of the time it will be 0, other half of the time it will be 1. This also is used for random number generation. That machine which USA uses to broadcast this random number uses this fact. Create the state in plus or minus or all the time plus, like 45 degree polarization. Keep on measuring in 0 1 basis. Half the time 0, 1 half the time 1. But any more measurement is uncertain. That is how random numbers are generated. So this fact that if it was 0, if you measure around plus minus, you don't find, the state is not there. You find state is there. And the superposition is like 0 plus 1. If it is 0 is yes, 1 is no, this object is maybe. So this yes, no, maybe, this kind of language came. Whether it's sunny, right, now, or rainy, or a mixture, sun, rain, sun mixture. This mixture kind of thing is called interference or superposition. This was not there in classical world. This actually came here. Now, any aspect have shown this kind of rotation is due to logic. In the statistics, people use this. A union B, these are the operators, kind of two operators you use, and you can compute. Bell's inequality is actually in the form of a expectation value, that's called probability, of two operators, sigma x, sigma y kind of thing. You take the Bell state, take these two fellows, multiply them, find out the average. This is the quantity. So mathematically not very difficult, but understanding is very difficult. Now you can see this Bell's inequality has created so much of excitement because it's actually manifestation of the quantum correlation at a long scale. Obviously, people will ask questions that you might have yourself in the state, which is called human choice. Now, so lots of loopholes exist. So many different kind of experiments are done to avoid this kind of loophole. And there are, Einstein pointed out that he did not like this idea of uncertainty. He said there has to be some local realistic theories where this probability, using standard statistical probability, things can be described. So this local realism is what Bell's inequality challenged, and so far quantum mechanics respects this kind of violation of local realism, and the non-local correlation like entanglement is there. But people are challenging it continuously. So this experiment, for example, one experiment to avoid human choice, amazing thing. What they did, they took like 1 lakh volunteers from all over the continent, located at different places, generating some random numbers based on which experiments are done. Experiments are done in different platforms like IBM quantum computer, whole atoms, everywhere they found that in a statistically robust manner is what it shows quantum mechanics is correct. So classical mechanics doesn't work. Namely, Einstein PR, what they suggested that local realism using classical statistical mechanics can describe things that doesn't work. The quantum thing. Now, what exactly is the difference between classical and quantum? Some of you who are familiar, classical thing depends on probability, positive numbers. Quantum has amplitude. So when you take psi1 plus psi2 mod square, psi1 and psi2 are amplitude. There you will have interference, negative number will come in if it is complex. Whereas classical statistics deals with probability, probability will never be negative. So probability versus probability amplitude. All positive numbers versus possibility of negative numbers coming because of interference. That is the difference between these two theories. All right. Now, so you now build big quantum computers. They're all made out of circuits which are entangled state. For example, here is a notation. Two particles are entangled. You do not denote it like that. The state psi is a Bell state. So you put a bracket here so that they are entangled. How did you create them? Okay, I created them just like I pointed out. Started with 0, 0, put a Hadamard, then control not, lo and behold, you have a entangled state here. Now, for example, in a computer, entangled state is there, calculation is proceeding, but how do you know environment has not destroyed it? Or some enemy fellow has come and touched it, so entanglement is gone. You are waiting for hours, no output. So question is, can you check that if the state is still intact, but if it's a computation which is going on, you should not disturb it, because if you disturb it, computation is gone. This was the first question I asked, and this engineering boy, electrical engineering, now he's with a multinational, he's with this Cadira healthcare in Ahmedabad, electrical engineer. He came for a 6-month project when I was in physical research laboratory Ahmedabad. We asked this question, and those were all of us were new, just learning to use Hadamard control knot. Measurement was old-fashioned, put an arrow. Now you see they put nice kind of D detector here, D. Oh, we use this old language, and we actually showed it was 6 months of hard work. Nowadays, if you do, you can do it very quickly. So what was the idea? Idea is that you start with the state entangled state representing a quantum computer. Bigger things can also be checked. These are the ancilla side lines with the register 0, 0. You take this 0, apply Hadamard, then do a control knot, and do another control knot, do Hadamard, you read it. If you find the output has changed you can actually see if 0 remains 0, then it is a state which is 0, 0 plus 1, 1 by root 2. If 0 becomes 1, it is 0, 0 minus 1, 1 by root 2. That means you can read the relative phase. Okay, here. You can find there if it is 0, 0, 1, 1, 1. So this is called parity. Okay, 0, 0. For example, you do control not operations from here and did it here, you will find out the content. 0, 0 or 0, 1 or 1, 1 or 1, 0. That will come out here. For example, if it is 0, 0, you can check yourself. Nothing will happen because 0, 0 control not doesn't do anything. 0 is 0. If it is 1, 1, nothing will happen because both are 1. One flow will change, the other flow will again change. So nothing happens. So 0, 1, you can check 0, 1 or 1, 0. The state will change. 0 becomes 1. So by measurement, you can find out. Here, the relative phase. Relative phase is called beta, I think. If I am whatever that plus minus sign, relative phase. If it is 0, 1 plus 1, 0, nothing will happen. 0, 1 minus 0, 1, 0, the flow will change. 0, 0 plus 1, 1, nothing will happen. 0, 0 minus 1, 1, things will change. So phase you can read from here. The parity, the content you can read from here. And at the end you see the state remains intact, nothing happens. So you can actually check if the state is there or not there by doing this kind of measurement. And the state remains intact, your computer is running, nothing is happening. So this information also give the kind of, it's like extracting information, phase information, parity information through measurement. This can be also used to check. Eve can also use it to find out about the state. So you have to be careful, but we used it to check if entanglement is intact or not. So actually, this was the preprint which we put very quickly. There are two other gentlemen came up with a bit generalized idea. All four of us combined it to publish. So this remained as a preprint. When Manu went to Bangalore to work for a private company, he showed this result to a very famous nuclear magnetic resonance experimentalist, Professor Anil Kumar, who did the experiment. 2011, you can check Jhananarani Das, Manu Gupta, Anil Kumar, and myself. It's an experiment which verified that what we have said is correct. So now you can use it for many things like error correction. We have used it for correcting errors. You can use it to detect if the state is gone or is there. Many things you can do. Now, as I told you that when the checking takes place, that takes place by looking at entangled states. How do you create it? That's an elaborate procedure. Okay, the molecule that was used here is chloroform. Chloroform, which is used to induce consciousness of human beings, is the molecule which NMR use for quantum computation. It's a big molecule. Two of parts you can entangle them. So that's what they do. This is the procedure how they create. So they start with a three-particle state. One will be ancilla, other two are the resistors. These two are used to create the well state. Then they call it something called pseudo-pure states. Because creating a pure state is not easy. You can essentially have to deal with differences on the background. So don't get into details. Only thing please remember that phase information, parity information has to be extracted. The state has to be created, and starting from register where everything is 0, and here is the ancilla on which reading will be done. Now, as I told you, there are two different ways of doing it. One is like in IBM, use superconducting qubits, or like D waves, use these magnetic moments. You see, these are the magnetic moments. They used Ising, NMR, these kind of things. Nuclear magnetic resonance naturally appears. So NMR people have been studying this kind of thing left and right. Here this I stands for 1, 0, 0 minus 1. And there are three particles, 1, 2, 3, because 1, 2, 3. That's it. It is. This is the energy difference. If you remember, minus mu dot V or I dot V is the Hamiltonian energy difference between two levels. And this is the interaction. Two spins are interacting, because without interaction, you cannot do anything. It's like control not, but it's more general interaction here. And using this simple Hamiltonian, D waves have implemented all the quantum computation. Now, this was NMR, nuclear magnetic resonance. D wave depends on superconducting qubits. Any complicated looking diagram. So you start with your state, do some operation to create well state, then encode your phase and parity, then finally read it. And this is the answer, and on which you read on this subject, you will find out the answer. This reading is done. This is NMR's way of showing a measurement. Once measurement is done, you get the output. Control 3 1, 3 is controlling 1. Control 3 2, 3 is controlling 2. Here the control gets. NMR people use various kind of pulses to create this. Fairly complicated, but they have been done, and this is if somebody is curious, so read this paper, Jaranamani Samal and others are there, Journal of Physics V 2010. You can actually discriminate Bell states without destroying them. Okay, nuclear magnetic resonance, pseudo pure state. Here the language. Now, then you may ask, too complicated. Can I come up with simpler versions where these things can be done, quantum information can be processed, measurement can be done? That actually brings these kind of states using light. So you can in fact use light. You see, this is something called Wigner function. And you can actually, this looks like a circuit, like a quantum circuit. You can actually create complicated looking circuits very accurately using interference phenomena coming because of light, laser light. One of these examples, this can be used like a network, okay, where you can put bits, you can carry out connection between them. You can also use it for other things. These are all examples of very famous states. Schrodinger cat paradox. I'll tell you a little more than that. The Schrodinger cat state is simultaneously exists here and there. Superposition kind of thing. 0 plus 1. 0 is here, 1 is here. Now, interestingly, when there's a cat state, there is some interference effect. You see, it is coming out here. So, particle nature, because the particle is here, wave nature, because of interference, minima and maxima, those things come out very cleanly in something called a Wigner function, W. So, once quantum mechanics came, Wigner was not very happy because he found XP don't commute. His point was, can I come up with a description which does not need commuting, non-commuting variables? He came up with something called Wigner function. So Wigner function, you can represent everything as a function of x and p, and it is actually x and p are normal variables, like x and p, no commutation. Then these are also Wigner function. Now, then you may ask, so where is quantum? Quantum is there because Wigner function is not a probability distribution. It can be negative. So this negativity of the Wigner function leads to thing. And you see here, negative starts from here, minus 2.3. You see here, black, negative, blue, this object here, negative, extreme negative. So the interference phenomena leads to maxima, minima, maxima, minima. Okay. The extreme minimum is here. This is possible in a quantum world or with wave phenomena where there is addition and negative side may come in. Now this object is called a quantum carpet. Obvious name because this looks like a carpet. So you can use quantum mechanics to design a carpet, okay, and design nice pictures. This is also used for measurement called metrology, quantum metrology. You can check. This is only 2019 paper, very robust measurement, and you can also use it for localizing particles. Particles can be localized here to design quantum circuit. So, for example, so this is an example which is only very recent. And cat state, you can use it for explaining paradox, like Schrodinger did, dead or alive, or you can use it for computation. You can search in the Google, you will find out cat code. It has been shown again in 2017-18, which people are designing experiments now, that this cat state can be used for quantum computation. This is in fact the first example of a continuous variable states which have been used for quantum computation. So far, we have been using only discrete variables, the ones which I showed you. Okay. So now, let me show you where are we right now. Quite a bit of progress has been done. For example, right now, major progress is coming from China. So they have actually teleported up to 1400 kilometers through optical fibers. So goal is to have a global, quantum internet. You can actually search in the web. You can find out there are already designs exist for quantum internet. So now people are using it optical fibers. So although right now people are using superconducting qubits, but the research is on silicon and light to design use good old silicon to come up with quantum chips, which can carry out things very similar to what is going on right now. So you can check J.W. Pan. So now he is the key person who is driving the quantum technology, and China has a lot of remarkable experiments. Satellite-based quantum computation, quantum teleportation. The name of the satellite is Messias satellite. Okay, it's stationed above in a geostationary orbit, 500 kilometers above China. These are the two cities situated between this and Tibet, Lhasa. So this is the teleportation. Now, quantum key distribution for secret exchange of messages was achieved at the level of two continents, from China to Vienna, Europe. Okay. So now, you can see secret messages between the supervisor, Geilinger, and student, Tan. Tan was guiding a student, took place and across continent through satellite. So you can see these are the quantum parts, very small quantum parts. Beam splitter, see photonic beam splitter, prism, polarization beam splitter, prism, same good old equipment which you have seen in optics. Say half wave plate, quarter wave plate, BBO crystal, same kind of thing, extremely pure form, single photon level accuracy is what is being used. But the optical elements are pretty much what you are familiar with. And laser light, these are basically light, and goal is to produce silicon and light kind of combination where quantum level processing can be done. Lot of progress has been made. Okay, you can see this kind of circuit. So you will have, you bring particles. See, this is Anton Zeilinger, Austrian scientist, president of Austrian Science Federation. You can check. Faculty, is quite old, I think 76, 78. Almost every year he used to come to meet Dalai Lama. I have met Zeilinger personally because I had gone there to review their quantum computation program in 2018. They got people from all over the world, 6 experts, to see where they are and how much money they need to make progress. So project, review kind of thing. Nice person, good group, a small group doing remarkable kind of work. So these are the kind of works you can see here. This is a paper, 2019 only, very recent. Same optical element, which I was telling you, has been used but the accuracy is at the single photon level. What they have done, so far I was telling you qubit 1001. They created qubit, 3 of them, trit 100, 00, 010, 001, and with accuracy of 75%. Fidelity shows accuracy, how accurate, truthfulness, fidelity. Now take teleported qubit. So this is the apparatus using laser light, orbital angular momentum to do all this processing. And here is the mathematics. Not very difficult. Superposition state, you see. Superposition state. Root 3 the normalization. 3 states which have been here. Now multiport, 3 input goes in. And then outputs come out. 3, 3, 3. So in total, 12 qubit states have been used. And you encode classical information and send. So this is the procedure, how to do it, how to create entanglement, how to code. Mathematics wise, you can see here, it's just a column vector, and processing is 3 by 3 matrices. Nothing very big. Mathematics is fairly simple. Difficulty lies in experiment because they have to be very accurate at the level of single photons. So that is the reason only in very few places these things are going on. In India, for example, Physical Research Laboratory, Raman Research Institute, Tata Institute are beginning to go there. But this level of accuracy is still to be achieved. We are still quite rudimentary in our laboratories. All right. So this is the first technology. Bennett and Brassard were in Bangalore, okay, having a beer when they heard about this measurement leading to collapse. So then they said, can we use it for some technology? And which would avoid, because Eve was trying to break in, can we avoid Eve? So they found out, yes, you can do it, provided you use measurement very nicely. So randomly using a classical random number generator, come up with 0, 1, 1, 0, just from your own mind, write this chain. I am, somebody called Alice. Just write it randomly, whatever comes to mind. Then decide the base. For example, computational basis or this 45 degree. You see, 45 degree rotation is this. This basis is up and down, 0, 1, 1, 0. And you measure. Only using this measurement and collapse and communicating through a classical open channel, in fact, actually, you can find a key. In this case, for example, 1011. Just measurement and checking the output. Measurement in two bases, up, down, and 45 degree and 135 degree. Nothing more. Just read about it, nothing more. You can actually find that you can check if it is present or not. At the end, you can come up with this key 1011, which is completely secret. Nobody knows. That is where quantum plays a big role. That if it is secret, it means really, really secret. Only shared between addition and bound. So she can now encode her message by adding this. He can decode it by subtracting this. Okay, as simple as that. So this QKD, quantum key distribution protocol, Bennett Brassard 84, was done over glasses of beer in Bangalore. So India has come up with the fast technology, idea of the fast technology. Now these things is actually available in the market as a technology. Now where was it first employed? It was employed in the South Africa football match. I think 2008 or something. This World Football Federation that every 4 years they have that football game, so that betting can be avoided. So that time where they first used this quantum channel for communication. Now, for example, this communication, even in India, many of the defense communication between important personnel, America, everywhere takes place through this kind of things. For example, India is also collaborating with Canada to come up with a communication satellite-based protocol. Lot of progress has been made to implement these kind of things. First application and manifestation of quantum technology. Of course, quantum computer is there also. Okay, so these are the kind of apparatus which is used, and through satellite-based communication. Again, this Chinese group have shown in the research paper that long distance 1400 kilometers and actually 1200 kilometers. Now, okay, now you can see that the experiment which are actually used, and as I told you, quantum experiments are very funny. The moment you measure, things will collapse. Collapse means state is gone, but there are ways. So it is this gentleman who is now around 90, Aronov, who came up with Bohm-Aronov effect. They showed that in 88 that you can actually carry out a very interesting kind of measurement, which was known in the second chapter of quantum mechanics called Storm-Gerlach experiment. You can actually do in a clever way so that the state doesn't collapse. You can extract information partially without collapsing the state. Very important development. This is called weak measurement. The new concept which has come, people are now using. But the experiment is same. Second chapter of quantum mechanics, Storm-Gerlach experiment, measuring spin, except interpretation. It was such a remarkable interpretation. The first paper was Aronov Weidman, and with other person there was another guy. Second paper was by George Sudarshan and his collaborators, showing that this method is actually physically meaningful. Now this is being used. Okay. Now let me show you that now quantum computers are there everywhere. Primarily, is being used by a lot of chemistry people. You just see every chemistry lab is now having a group dealing with quantum computation. Why do they need it? Because they need to compute their energy eigenvalues very accurately. Right? For example, very, very accurately. So that is where they need a quantum computer. Whenever there is a big computer machine comes out, first machine is given to atomic physics people and to carry out the energy level calculations and see how accurate they are. Why is it? Because experimentally you can measure their accuracy. So for example, when I was doing my PhD, the person who was leading this group was from Odisha, Dr. Mohanty, PhD in atomic physics, and I asked him that how come you are there? You are an atomic physics person. Then he explained to me that nature has an accurate, quantum computer, quote unquote, big atom like uranium. It gives you the spectroscopic levels which you can measure very accurately. So every time you are exciting, it is calculating and giving you numbers. Now you make a powerful computer. How do you check? Just do the calculation on your computer, check what numbers you are getting, match with experiment. That's what they do, and that's what certifies that a computer is powerful or not. Then you may ask, if classical computer was doing it, what are you doing in this? Answer is that yes, classical computer was doing it. It can do it with lengthy programming and part of the information, because typical quantum process can be done much faster and much more accurately, in some cases only exactly, by a quantum computer. Who gave this idea? It was Feynman. Feynman actually came up with the idea of quantum computation in 81-82, pointed out that difficult problems, like for example strong interaction, confines quarks inside an atom, proton, can be checked only using a quantum computer. He was the person who also pointed out that information, infinite amount of information, can be stored. So it was only 80s, and this is how the technology has moved. And these chemistry people, of course, people are using quantum computer to get some idea about strong interaction, but primary application now is in chemistry. Was very accurate. The first paper in chemistry, I think 2011, was you can check that one Indian person boy was there, son of out of Sachari, IISERKolkata director, Khandala, if I remember is correct, Abhinav Khandala, if his name is correct. First paper, big molecules, ground state energy, they computed. VQE, variational quantum eigenvalue solver. You can actually use it. Our students are also using it. It's a platform open for everybody. IBM actually teaches. Presently, they are teaching various programs. We have this workshop called Quantum Information Quantum Technology 2021, where the last 5 days, 5 of their experts are coming and teaching. We are actually conducting tutorials how to use IBM quantum computer platform to carry out quantum computation. Some of you who are interested, you can actually check it out. Just go to QIQT, Quantum Information Quantum Technology 2021.org. All the program is there. You can actually log in. YouTube, the program is broadcast. You can actually see. So these are real machines. Now, in India, as I told you, Physical Research Laboratory, Raman Research Institute, Professor Urvashi Sinha, they are actually, there's a collaboration with Canada, satellite technology, checking out. They have come up with a quantum key distribution protocol. Now, these are the kind of efforts which are coming from India. Okay. Now, after Feynman came up with this idea, still quantum computer was nowhere in the scene. So early 90s, there were two major developments. One of them was by our Indian scientist Love Grover, who pointed out that you can actually solve a search algorithm. You can search very effectively using a quantum computer. It is called Grover's algorithm. And he is a classical physicist. He knew only 2x2 matrices. You talk to him, computer science person, born in Mesra, very decent person. And he did not know anything, no quantum, only 2x2 matrices. But he showed that using that, you can actually search very accurately, much more powerful. Now, Google search engine is there, of course, but people have shown this is the most powerful one. This actually has found practical use. Many people believe that nature uses this kind of search algorithm. For example, in photosynthesis, when light falls, it is directed towards the reaction center, people claim, through this kind of methods. So biology, photosynthesis, quantum, coherence has manifested, but people are still searching. Many people believe these birds, for example, when they navigate, their brain basically keeps track of the direction through the magnetic field. That is a quantum process. But a lot of work is going on right now. So this was one of the first. The other one was this factorization. Peter Shor, SHOR. He showed that give me a quantum computer, any big number I can factorize. What does it mean? You can actually break codes. So any secret message exchange, you can actually read it out. So that is where people woke up and started pumping money, late 90s, into quantum computation. Who pumped money? Make a guess. Central Intelligence Agency, CIA in USA, and Swiss Bank in Europe. Why? Now you make your own choice. CIA, of course, needs it because they have to keep messages secret. Swiss Bank, Why they need? You can see the newspaper yesterday, lot of new Swiss bank accounts which have been opened and everything is secret. Okay. Now lot of things are now coming. For example, Google showed a quantum computer is truly powerful, called quantum supremacy. The lead person's work which led to this is Mesra, a computer scientist, University of Berkeley. So he is one person whose students and him are really, driving this, designing of algorithms, trying to show which thing where quantum really can do better, where the quantum cannot do better. One example is Google made a lot of noise. Actually, Google spelling is wrong. Supremacy. So quantum supremacy, so that a quantum computer really is powerful, is what is game right now. In some cases they are not, because apparently in case of cryptography, secret message sending, people have gone beyond quantum, something called lattice-based models beyond quantum. So it's not guaranteed that a quantum computer will be doing everything efficiently. All right. Now this is IBM. I have been mentioning IBM machine many times. This is one example of a prototype. It was built by this one faculty member from Yale. In Yale University, they championed this kind of technology, superconducting qubit-based technology. And so this person, gentleman, associate professor, moved to IBM. He's leading that group now. So they are one group which has been spearheading this area. 5 or 6 of their computers are available. We have been using them left and right here without paying any money. Their language is called Qiskit. They're making it very popular. So now freely available. Now Google has come in a big way. You might have read in newspapers. There are private companies, for example, this ID Quant, Toshiba, Magic. Yeah, so I'll take 5 more minutes. Now, if you ask money, this is in sterling, I think. Around, QKT machine is a bit expensive. Random number generator, quantum random number generator, EGG. They look like this. Now, so you can buy things. It is this NIST which is broadcasting quantum random numbers. You can actually check it out. So a lot of things are now available. You can actually see a quantum computer. All right. Now, as I showed you, either you can do computation using qubits or continuous variables. These things are becoming popular now. So for qubits, you can use photons, you can use quantum dots. Detection mechanism is different. You have to use light, like single photon kind of thing, very weak light. And so these are the kind of things which you have to use. Controller, Pauli operators. Now continuous variable, mode of detection is different. So what are the kind of things? Quantum modes, Bose-Einstein and condensate, different way of detecting it, bright source of light. So these kind of names, coherent states, quiz states, number state, beam splitter, these are the kind of machineries which are used. So though both the languages, you will find fairly commonly people going back and forth between these two. So now Wigner function is the one which I used. For example, squeeze state and coherent state, cat state, they are the kind of states which are quantum states. This object coherent state is completely classical, laser light. And this thing was first done, shown this property of light, what is classical, what is by these two gentlemen, Sudarshan and Glauber. Glauber got the Nobel Prize, for which many people are still debating that Sudarshan also should have got it. Passed away a few years back, did formulate the theory of weak interaction with Marshak. He then lost it because 4 authors, Feynman and Gell-Mann, apparently they don't give to 4 people. The basic theory of interaction we did not get Nobel Prize is weak interaction. Electrodynamics, Feynman, Swinger and Tomonaga got strong interaction. Gross, Pollinger and Wilczek got only weak interaction was left out. Again, laser light, quantum optics, both the persons gave the theory and again he lost out. But anyway, his contribution is how to create a classical state from quantum. Coherent state is classical. That is of course going to live on. Okay, so now what kind of things they measure? They call it quadrature. They are coordinate and momentum. This field, coordinate, electric field and its momentum. You can cast it like coordinate and momentum. Everything follows using only standard these things. Now, just like IBM using qubit, light-based softwares and simulators are available. This Jandao is the one which is available freely. They use all this optical light kind of thing for simulation. So this is also privately available. Now, so the mathematics is slightly different. You deal with phase space, displacement operators, but this is the thing they are trying to popularize. It's a bit more complicated. That's what students tell me. This Jandao thing, but it's a simulator which is available. All right. Now, this is just simple mathematics. People try to create quantum light starting from coherent state, doing some squeezing. What is squeezing? You try to decrease uncertainty in one of these x or p variables, and you create squeeze state. Why are they useful for? They are useful for metrology. Gravitational wave you can detect very accurately. Yesterday, Professor Agarwal gave a nice talk. G.S. Agarwal, one of the pioneering experts, is there in YouTube. So QIQT, you can check it out. He was actually showing what is the world status right now in generating squeeze light, what kind of measurement you can do. There also people are using quantum computer. Other is this Schrodinger's cat state. Now the cat state has been created 2018-19 in a way where you can manipulate and do some quantum computing. So-called cat code has manifested only a few years back. So the thing which was used to sort of come up with an idea about EPR paradox is now finding technological applications for that for quantum computation. All right. Now, any quantum thing you do, you should show that state is non-classical. How do you show that? Linear function is the best approach. But I can tell you that still there are a lot of debate is going on. It is nothing is settled. Linear function becoming negative shows non-classicality. But nothing is settled yet. There are squeeze state is non-classical, but it is positive. So negativity of p function shows non-classicality, but there are examples where this may also fail. So going from classical to quantum, quantum to classical, how it happens, we still have a lot of debate going on. So if you see Bohr's correspondence principle, wave function collapse, still we are debating, but experiment is happening. Classical quantum correspondence exists, but we are still debating and finding out how it works, how it happens. Somebody thinks about consciousness, big people like Wigner, that the human consciousness which collapses. For example, people talk about gravitation. Gravitation is intrinsically connected with collapse of wave function. So, Roger Penrose, who got Nobel Prize last year, 2020, he thinks that way. So you can see all the debates are still going on, but people are beginning to use quantum mechanics for computation and other applications. All right. So I know coherent states, for example, are not orthogonal, yet they're useful. I told you 0, 1 are orthogonal, but here is an example which is not orthogonal, but still they are useful. Now, how do you create them? You create them using light. That is laser. All right. So these are the parameters which you basically use to characterize them. Let's not get into details. Okay. So Wigner function. And now I'm not getting into mathematics. I think you can create different kind of states. Now people are actually creating by putting this relative phase, which is different. Okay. Now quantum metrology you can do through interference. Here are beautiful examples of Keaton state. This is the so-called Keaton state. 4 places localized. Cat 2 place. They have actually been produced experimentally. Cat Keaton. So these are the kind of pictures which are now beginning to emerge. Now, how to check something is quantum? There was a beautiful experiment in 1957 called Hanbury-Brown twist. They pointed out the light which comes from star is actually quantum. How do they check? They looked at the fluctuation. So you can actually estimate size of the star, size of the nucleus using this by looking at the fluctuation, number fluctuation. Amazing. Routinely used for HBT, Hanbury-Brown twist. That is how Sudarshan came into laser light, and that is how he showed that it is classical. So star, this Hanbury-Brown and twist, they did the experiment in Australia in 57, looking at the star light, how it is fluctuating. 2 nature papers, one applied mathematics, one radiophysicist. That is how this thing came to characterize light, looking at the statistics. So there are parameters which can actually check out the variation, small subtle differences You can see here these three are identical here. But in low photon number at the quantum domain, they differ. So these kind of experiments people are actually carrying out now. Now, cat kitten states are experimentally possible. So nice. You can do, I mentioned your Lewis measurement. You can extract information without fully destroying it. If some of you are interested, the references are here. Now, for example, other state, there is something called cluster state and highly entangled particle involving a lot of particles. You see 2019. Actually, there are two places in Denmark Technological University and also Tokyo Institute of Science and Technology. They have produced this kind of state, so-called cluster state. All right. So now, this is our Chinese group. This paper just came out in, I think, this 2021 in Science. You can see huge laser lights have been used to show that quantum can do something much better than classical quantum systematic. Just Chinese scientists, 2021, paper in Science. You see the kind of apparatus that is there. Okay, so now this is the chip, Google chip. This is Sycamore chip, Google quantum processor. Okay, now I will not show you any more pictures. Basically, 1 photon, 2 photon, 3 photon, different phases. People are doing boson sampling problem. It's a very important problem. People are basically searching for problems where a classical computer cannot do, a quantum computer can. Okay. Now, during the shutdown period, lot of experiments are done without much of interference. Now, private companies are coming into play. You see, Singapore has a company, all are designing into satellites, quantum chips, and communication. Communication is the key. Okay, then you may ask that can I do something myself? I'm a small fellow. You can check. There's a girl, Yuin Chan. Search for Yuin Chan. As a high school student, is solved a big problem. So you knowing your simple mathematics, you can still do something which is unusual and new. 18-year-old girl, Yuin Chan. Check her out. Now, if you are a computer scientist, can you do something? Answer is yes, Urmila Mahadev. She asked this very simple question. A quantum computer is there. How do you check it's a quantum computer? 8 years of work, one paper, and she solved the problem. Okay. Now, where are the Indians doing? You can check. Indians are playing a big role. For example, there is a network coming up between, Fermi Lab, University of Chicago, then between Ohio and Washington. Who is building it? An Indian person. That I leave it to you. Find out who is the person who is doing it. He is from Evanston. Okay. So this project is on. So I thank you here. Lot of efforts are on in India and abroad. Government of India has a project called Quest, Quantum Enabled Science and Technology. There is budgetary allocation of specific amount for quantum technology. Hopefully, many of you will guide younger people to get into this area. Thank you. I'll stop here.
Thank you so much for your wonderful insights on quantum computing and technology. Now, I request our participants, anybody having any queries, please unmute and ask your questions.
Yes, sir.
Yeah.
Yeah.
You can ask.
Sir, these measurements that we are doing, they can have some errors also.
Yeah. There are
So how?
errors.
Yeah.
There are, you are asking about errors, right?
Yeah, errors in measurement.
Yeah. See, there will be error in when you register, when 0 becomes 1 or you put a 0 there, that is called initialization, there will be error. Readout, there will be error. Hadamard gate, for example, IBM, if you go, they list those kind of errors. Hadamard gate, how much error it has. Control not gate, because it involves two of them, has more error. All of these are error prone. Therefore, the present idea is to compute and see efficacy in this noisy environment. This is called NISQ, noisy intermediate scale quantum computing. Noisy intermediate scale quantum computing, NISQ. That area, that time is going to last for, people are suspecting, 8 to 10 years. So whatever you find right now, people are trying to show in this environment, still can you answer something? Answer is yes. Still you can do something. But things are going to improve.
Yes, sir. Thank you. Thank you.
Sir, thank you, sir. Here, question is here.
Anybody else?
Yeah.
Who
sir,
is that?
this is
Sachin.
Desikan. Hello.
Srinivas.
Okay, you can
Hi,
ask.
yes,
You can ask.
may I ask
Yeah,
a question?
thank you, sir. Thanks for the time.
Yes.
Sir, thank you for your wonderful presentations
So,
about the quantum computing. Uh, I think the question is, I am the basically computational chemist. As you also pointed out, chemistry people are using this quantum computing very nicely. Still not we are not using, but actually in my case, we are using the classical computation still. We are as a computational calculations for the atomic level. As you also mentioned that some of the people are doing it Orisha, right? So for any barrier energy calculations or any kind of scientific things for atomic scale, we are doing that. The question is, in the classical computer, there is some limitations for the number of atoms. We cannot go for 100 or 120 atoms. There are some limitations. How about the quantum computation? If I use the computational quantum computing, is it possible to overcome this issue, or still that issue is some limitations are there? Thank you.
No, see, for example, there are limitations. Here, IBM has different versions. Initial had 5, so for example, the D waves, they have made it quite big, thousands of the order of thousands. Google has some 52 or something. There are limitations in number. It depends on the machine. IBM has 4 or 5 versions. If you pay more, then of course that paying fellow has some more, around 60 or something. And the ones which are freely available, 15, 20, that kind of things. So there are there is a ion cube quantum computer, I think 20 qubit. So there are, there are limitations there, significant limitations.
It depends on the computer, or it has some different methods also available. We can use it and enjoy that number of overcome this issue.
No, it depends on computers. The platforms which is available, you can actually check IBM Quantum Experience. There are 4 or 5 versions. 2 of them they are shutting down now. Depends on machines actually.
Okay. Is there any platform
in that machine also, some of the qubits are more error prone than others.
Okay.
So that also has a limitation.
I see. Is there any free platform for the academicians can use this, enjoy the quantum computing?
Yeah. In fact, we are doing here in Mohanpur, in IISERKolkata. Since last 4 or 5 years, we are doing it. I am sharing my email. If you are more curious,
sure, definitely.
panigrahi.iisr@gmail.com.
Okay.
PANI. Sridhar can share it with you.
Yeah,
sure.
I'll share it. Okay.
Sure. Thank you, sir. Thank you so much.
If you have time, we have this WhatsApp going on right now, month long, QIQT-2021.org. Please log in. YouTube talk you will find for free. You can attend going on up to 16th of July.
I see. Sure. Definitely, sir. Thank you for the information.
Thank you.
So next question is from Sachin. Please go ahead.
Yes, sir. Yes. So thank you for this excellent session. During your session, you mentioned about the importance of Hamiltonian to convert real-world problems to be solved using a quantum computer.
Right.
Can you just brief on how to convert a problem into a Hamiltonian?
Okay. See, these are the ones which are done by NMR people, NMR quantum computing, and also this D waves. So what they do is that, for example, you have a interaction, spin-spin interaction. Okay. So in that coupling and in the magnetic field, amount you make according to the problem which you have had. If you actually send me an email, I'll send you a paper where 15 is equal to 3 times 5 has been solved. How they have encoded that 15 now and how 3 and 5 comes out. But you can actually do. There are operators. Don't go anything with operator. It is the coefficient of those operators which are changed. And how long the evolution takes place when you start reading, that also has information. Using these 2 channels, you can actually do. Yes. It is possible. 15 is equal to 3 times 5. That example I can send you.
Yes. Sir, I have another question. You mentioned about the importance of complex numbers in quantum computing.
Yeah.
Can you just elaborate on that particular point? Especially, you mentioned that interference is not possible without complex numbers.
Yeah. See, for example, see this actually it's a little bit of exaggeration because quantum mechanics needs complex numbers. If you look at, for example, light, circular polarization is actually the state of light. It carries angular momentum, not linear polarization. When it is emitted, it is circular polarization. What is circular polarization? It is actually Ex plus IEY. I is there. Exponential I theta, exponential minus I theta, they are the state azimuthal quantum number. So quantum mechanics or circular polarization intrinsically needs complex number. Okay. You can't really avoid it. There's a very beautiful recent paper which shows by you can search MACCONE, MACCONNE. Okay, that shows that I is required.
Okay. Thank you, sir.
Okay, yeah.
Anybody
So I'll log
else?
out.
Okay, thank you so much, sir, for giving your valuable time and given a nice talk on quantum computing and technology. So hope the participants have really benefited from your talk. Thank you so much, sir. Take care. Namaskar.
No, sir.
Namaskar, sir.